This lecture is about error control coding. Here, let us see convolutional codes. Basic terminologies are: L is the length of the message sequence, M is the number of shift register, small n represents the modulo 2 adders, and code rate is given by R equal to L divided by n into L plus M. Typically, L will be very greater than M, and so this L plus M will be approximately equal to L, and thereby the code rate is given by 1 by N. Let K be the constraint length, which is the number of shifts required to influence the encoder output. Once a message bit is given at the input, the number of shifts required by that message bit to produce the change in the output, to produce a change in the encoder output. For example, let us take n equal to 2 and k equal to 3, and thereby the code rate is R equal to 1 by 2. And let us assume initially the encoder operates over one message bit at a time. Look at this example. Here there are two flip-flops given here, and the number of modulo 2 adders are 2. One message bit is taken at a time, and the output, since there are two modulo 2 adders, will be a multiplexed output from path 1 and then from path 2. So this is a rate 1 by 2, constraint length k equal to 3, since there are two flip-flops are there. So it is a rate 1 by 2, constraint length k equal to 3 encoder. This is another convolutional encoder where rate R equal to 2 by 3. Two input bits are processed at a time, and there are three modulo 2 adders, and thereby these three bits are multiplexed in order to form the encoded output. Here, since there is only one flip-flop on both this path, the constraint length is k equal to 2. There are three ways to represent graphically the output of the convolutional encoder. They are the code tree, state diagram, and the trellis diagram. However, we can describe the convolutional encoder by using this generator polynomial. Using the polynomial method, we can generate the code that is given here. This is doing pictorially, and here we can produce the encoded output using these generator polynomials. The general expression for the polynomial is given by g of I of d equal to g. How many ever number of paths are there, that we have to first decide. Let us take this example alone now. So in this there are two paths, one is the upper path and the other is the lower path. So we'll have two generator polynomials, g1 of d and then g2 of d. The general expression given for polynomial is g0 plus g1 of I into d, g2 of I into d square. It goes like that up to gm of I d power m. Here these d's indicates the delays or the flip-flops given in that encoder structure. So here this represents the coefficient from the flip-flop 1, that is the d's coefficient, and this represents the d square's coefficient. And thereby here for this encoder, the impulse response for the upper path is, that is the input to the modulo 2 adder is 1. Here, since it is coming from d, the second coefficient is also 1 and the third coefficient is also 1. However, the impulse response for the lower path, that is the inputs to this encoder or to this modulo 2 adder is, from here there is a path exists, so 1, and here from here there is no path exists, so here it is 0, and from here there is a path that exists, that is input is given to this modulo 2 adder, so it is 1. So here the impulse response is 1, 1, 1, and here for the lower path it is 1, 0, 1. And now coming to this polynomial method of encoding, the impulse response of the upper path is 1, 1, 1, and the impulse response for the lower path is 1, 0, 1. So the polynomial, when you write, it will be g naught of I, the coefficient is 1 here, since it is 1 here, you are getting that, and then the coefficient of d is also 1 here, so it is plus d, and then the coefficient of d square is also 1 here, and so you get d square. So the polynomial is 1 plus d square with respect to the upper path, and similarly with respect to the lower path it will be 1 plus 0 plus d square, 1 plus 0 plus d square. And now let us encode this sequence using a typical an example message sequence as 10011. Now you write the message polynomial m of d equal to, this is 1, then here the coefficient of d is 0, and then the coefficient of d square is 0, and here the coefficient of d cube is 1, so you have this d cube here, and the coefficient of d power 4 is 1. So your message sequence is now, for the message sequence 10011 is given in the form of polynomial as 1 plus d cube plus d power 4. Now multiplying in this generator polynomial with that of the message polynomial, first consider the upper path. In the upper path, the generator polynomial is 1 plus d square. So multiply that upper path generator polynomial 1 plus d square by the message sequence m of d, 1 plus d cube plus d power 4. This is the message sequence. Multiply these two. So what do you get here? 1, you multiply this 1 plus d cube plus d power 4 plus d power 4 plus d power 5 plus d square plus d power 5 plus d power 6. And since it is the modulo 2 addition, that is XOR addition, d power 4 plus d power 4 will be equal to 0. Similarly, d power 5 plus d power 5 will be equal to 0. So what is remaining is 1 plus d square plus d cube plus d power 6. And therefore, the output sequence here is 1 is here, d square, and then d cube, d power 4 and d power 5 are 0, so they are 0, and d power 6 is 1. So this is the output sequence generated by this upper path. So here, because of this modulo 2 adder, the output sequence generated is what we have seen now. Next, following the same procedure for the lower path, the generator polynomial for the lower path is 1 plus d square, and the same message sequence 10011 is taken. Multiplying that, we get the output sequence as 1 0 here. 1 d is not there, so it is 0. So d square, d cube, d power 4, d power 5, and d power 6. This is the output sequence, a coded sequence produced because of that lower path. That's a lower modulo 2 adder. And now at the output end, we have the multiplexer. Here there is a multiplexer. So you multiplex the bits, the coded bits generated from the upper path and lower path one by one. And so here is written the bits from the upper path, and here are the encoded bits from the lower path. And thereby the encoded output is 1 1, then 1 0, 1 1, then 1 1, 0 1, 0 1, and 1 1. So this is the encoder output generated by means of this polynomial method. moving on to these three methods, where because doing this polynomial method will be difficult once the number of message bits gets extended. So we go for any one of these three methods, which would be easy for computation. And first, let us look into the state diagram method. Using this state diagram, it would be easy for us to construct the code tree as well as the trellis diagram. Going to the state diagram method. First, assign the state for the assign the state of the encoder. Here in this encoder, we have two flip-flops. So there could be 4 states possible, and assign the name of the state for all these 4 states. Let 0 0 be represented as state A, 1 0 be represented as state B, 0 1 be represented as state C, and 1 1 be represented as state D. Now we have to form the state diagram will be in this manner. Let us now construct the state diagram using these state assignments. Now, when an input is applied, it enters that input is reflected in flip-flop 1. That's the rule. This is a rule which we have to follow carefully. When an input is applied at this point, it enters into flip-flop 1. The current state of flip-flop 1 enters into point A and to flip-flop 2. And then the current state of flip-flop 2 will be now available at point B. This is a rule which we have to follow carefully in order to proceed further. Let me repeat once again. When an input is applied at this point, that input enters into flip-flop 1. The current state of flip-flop 1 moves into point A and to flip-flop 2. And the current state of flip-flop 2 will now enter into this point B. Right. Let me write the state name here. 0 0 represents state A, 1 0 represents state B, 0 1 represents state C, and 1 1 represents state D. Now let us assume initially the encoder is in state A, that is all 0 state, 0 0. And now there could be two options. Input could be either 0 or 1. First, consider the input to be 0. So when an input 0 is applied here, then it enters into flip-flop 1, and now this flip-flop 1 state will enter into this point A and to flip-flop B, and the state of this flip-flop 0 will now be available at point B. It so happens, since the state is all 0 state, here also the next state is also all 0, and these are the state at this point. Now find out the output of this modulo 2 adder. Here it is 0, here it is 0, and here it is 0. So the output would be 0 plus 0 is 0, and 0 plus 0 is 0. So at the path 1, the output is 0, and similarly here this is 0, and here this input is also 0. So 0 plus 0 is 0, and thereby the output is 0 0. So when the encoder is in state A and when the input is 0, then the output is 0 0, and the next state is 0 0, which means 0 0 means it is state A. So I'm going to draw the state diagram. Let me start from state A. Assume here is state A. Assume here is B. Here is C. And here is D. Okay. And now I'm starting at point A, that state A. If I give input as 0, whenever I give input as 0, then it would be mentioned by the solid line. In all these three diagrams, if the input is 0, it would be mentioned by solid line. So when I give input as 0, my next state is A itself. So that means I can draw the state diagram like this. Okay, if I give input 0, my next state is state A. So it loops around. What is the output at that time? It is 0, 0. So I can write 0, 0 on the edge of this line on this side. So here, now I started with state A. When I give an input of 0, it remains in the same state, producing an output of 0, 0. Next. Next, for the same state 0, 0, let the input now be given as 1. This is input 1. So this input is now available in this flip-flop 1, and then this 0 comes here and also here. And then this 0 will be available at this point B. So here my next state is 1, 0, and my output will be, here it is 1, here 0, here 0. So 1 plus 0 is 1, 1 plus 0 is 1. So here it is 1, and on the lower part this is 1 and this is 0. 1 plus 0 is 1. So my output is 1, 1. So when I give an input 1, when my present state is A, it goes to state 1, 0. 1, 0 is B state. So it goes to state B and my output produced is 1, 1. So since the input is 1, I have to draw in the state diagram using a dashed line. So it will go to state B. From A, it goes to state B when I give an input of 1, and the output produced is 1, 0. Now let us move on to the next state. Here, now consider the initial state of the encoder as 1, 0. 1, 0. Now when you give an input of 0, here this flip-flop now becomes 0. This one comes here and this one is here, and this 0 will be here. So my next state is 0, 1. So if I give an input of 0, my next state is 0, 1, that is state C. So I am here in state B. My next state is C for an input of 0. So I am drawing a solid line. It goes here. My output will be, here it is 0, here it is 1, and here it is 0. 0 plus 1 is 1, 1 plus 0 is 1. So here it will be 1, and here it is 0, and here it is 0. So 0 plus 0 is 0. So my output would be 1, 0. So here my output is 1, 0. Now for the same state B, 1, 0, let the input be now 1. So this 1 will be available here, this 1 here, and also here, this 0 here. So what is my next state? It is D. So from B, it goes to D when I give an input of 1. My output would be here 1, here 1, and here 0. 1 plus 1 is 0, 0 plus 0 is 0. And here it is 1, and here it is 0. 1 plus 0 is 1. And so my output is 0, 1. So here my output is 0, 1. Now coming to the third state, that is state C. Status 0, 1. When the input is 0, here the state of this flip-flop is 0, here it is 0, and here it is 0, and this 1 comes here. And now my next state is A. So when I am in state C, and if I give my input as 0, my next state is A. So the solid line comes from here and it goes to A. The output would be 0, 0, 1. So 0 plus 0 is 0, 0 plus 1 is 1. And here, lower part, this is 0, this is 1, 0 plus 1 is 1. So 1, 1 is the output. So you can write the output as 1, 1. And now, when the input is 1, when the input is 1, then here it is 1, this 0 comes here, it's 0 here, and this 1 here. So my next state would be 1, 0. That is 1, 0 means state B. So from C it goes to B when I give an input of 1. The output would be 1, 0, 1. So 1 plus 0 is 1, 1 plus 1 is 0. And here it is 1, 1, 1 plus 1 is 0. So the output is 0, 0. And next state is D. D is 1, 1. So if I give an input of 0, here it is 0, here it is 1, here it is 1, and here it is 1. And so the output would be 0, 1, 1. Here it is 0, 1. So 0 plus 1 is 1, 1 plus 1 is 0. Here 0 plus 1 is 1. So the output is 0, 1. The next state is 0, 1, that is state C. So from D, when I give an input of 0, it comes to state C and the output is 0, 1. When the current state is D, 1, 1, and if the input is 1, here it is 1, 1, 1, and this 1 comes here. And so the next state is D. The output would be 1 plus 1, 0, 0 plus 1 is 1. Here 1, 1, 1 plus 1 is 0. So the output is 1, 0. So it remains in the same state when 1 is given and the output is 1, 0. And this state diagram is given here. Same state diagram. Taking this is state A. When an input 0 is given, remains in the same state, and here is state B for 0 and for 1. Here is state C for 0 and for 1, and this is state D for 0 and for 1. From B this is state for input 0 and for input 1. So from this state diagram, having drawn the state diagram, how to encode the message sequence. Take the same message sequence which is already considered 10011. Now start with the all zeros state. So you are here now. Presently the message bit is 1. So follow the state when the input is 1. So here when it is in state A and when the input is 1, it goes to next state as B and the output produced is 1 1. So here the output produced is 1 1. And then you are here now. The next message bit received is 0. So follow the solid line and the output is 1 0. So now we are in state C and the output is 1 0. And now the next message bit received is 0. So from here follow the solid path. It comes to state A and here the output is 1 1. So it is 1 1 and now once again you are in state A. And now the message bit received is 1. So 1, you follow this dashed line, it goes to state B again and the output is 1 1. So here it is 1 1. And now from B you have the message bit as 1 and so follow the dashed line, it goes to state D and the output is 0 1. And now you compare this output with what we have already obtained using that code polynomial. It would be the same. And now the path followed was first it is A, then you went to B and then it was to C and then to A and here to B and finally to D for the message sequence taken as 10011. This is a path followed. So once you draw the state diagram, it is easy to encode without going for those polynomial computation. From the state diagram, now you know what is the next state when an input 0 is given and when an input 1 is given. Given a particular state, you know what is the next state when an input 0 is given and when an input 1 is given. Based on this information, now you can draw the code tree. The basic rule to be followed in code tree is to draw the upper branches of the code tree, consider the input as 0, and to draw the lower branches of code tree, take the input as 1. Let me repeat. To go up in the tree, take the input bit, the message bit as 0, and then write what is the corresponding output and the given state and the next state here. To draw the lower branch of the code tree, consider the input bit as 1, find the next state and the output and draw the lower branch. Now, we are here in the root. First, as usual, consider initially the current state of the encoder as 0 0. That means we are in state A. When you are in state A, let me just bring this state diagram here for convenience. Right. Now, now we are in state A. If the input is 0, remember once again, if it is 0, you have to follow the solid line. If the input is 1, you have to follow the dashed line. So if the input is 0, then it remains in the same state, producing an output of 0 0. So here, when the input is 0, that means we are traversing up in the tree. and here the output is 0 0 and the state encountered is A. And now you are in state A now. To traverse lower in the tree, let the input be considered as 1. So follow the dash line. You go to state B and the output is 1 1. You go to state B and the output here is 1 1. Okay, now to travel up in the tree from this point, once again go to the state A. If you give an input of 0, then you will remain in the same state, producing an output of 0 0. So you go up. Whenever you are in state A, if you go up, you can see that you will be in the same state A, producing an output of 0 0. Similarly, from here also, if you want to travel up in the tree, you will be encountering the same state A, producing an output of 0 0. So from here to go up in the tree, you will be in the same state A, producing an output of 0 0. Right. Now from here, let us try to come down here in the tree. So from state A, when we are coming down, that means we give an input of 1. So from A, if the input is 1, follow the dash line. It goes to state B, producing an output of 1 1. So you are coming down, that means you are encountering an input of 1. So you are coming to state B. You are coming to state B, producing an output of 1 1. Right. Now you are currently in state B. Here you are in state B. To travel up in the tree, you have to take an input of 0. So from here, if an input of 0 is considered, follow the solid line. You will come to state C and the output is 1 0. So to go up in the tree, consider the input as 0. So you go to state C, producing an output of 1 0. And now you are in state C. From state C, if you have to go up, that means the input should be 0. So that means you have to follow the solid line. Follow the solid line. You come to state A, producing an output of 1 1. So from here, you go to state A, producing an output of 1 1. And then from this point, since this is point A, this is state A, so if you go up, that means if you encounter an input of 0, then you will come to the same state A with an output of 0 0. Right. And now from this point, okay, we'll see from this point, from state A, if you encounter the input as 1, then you come to, if you encounter an input of 1, then you come to state B, that is 1 1 with an output of 1 1. So you come here. So whatever we saw in this lower, it will come here. So you come to state B with an output of 1 1. From B, if you take 0, the next state is C with an output of 1 0. The next state is C with an output of 1 0. Then from B, if you take 1, then you go to state D with an output of 0 1. So if you take up 1, you come to state D with an output of 0 1. And then, so from state C, if you take an input as 0, then the output is 0 1. From state C, if you take the input as 0, then you come to state A. If you come from C, if you take an input of 0, you come to state A. It's not given here. This will be actually state A, and the output is 1 1. So it goes like this. If you want to come to the lower branch from this C, then you have to take an input of 1. So you go to state B and the output is 0 0. You go to state B with an output of 0 0. So you have to go like this throughout the code tree. So you have the state diagram with you. To go up from any point of the tree, consider the input to be 0. To go down in the tree, take the input to be 1. Then find out what is the next state and the output from this state diagram and mention it in this code tree. Having constructed the code tree, how to find the encoded sequence? Let us take once again the same message sequence. consider the same message sequence 10011. Start from the all zero state. The first bit is 1. So come down the tree. Here, come down the tree. What is the output? 1, 1. Written here. Then you are at this point now. What is the next message bit encountered? Is 0. So go up the tree. What is the output? Here it is 1, 0. So produce that. Write this 1, 0 here. And now here at this point, the next bit received is 0. So go up the tree and the output is 1, 1. And here the output is 1, 1. You are at this point. And then the next message bit received is 1. So go down the tree and the output is 1, 1 here. And you are at this point and the next bit received is 1. And so go down the tree and the output is 0, 1. Output is 0, 1. So in this way you can traverse a tree and find out the encoded output. And now when you look at this code tree, you can see that when you look at this code tree, you can see that the states repeat after the third branch. Here you can see the next states are A and B. Here A, B, C, D. And here A, B, C, D. Here also A, B, C, D. And here you can see A, B, C, D, A, B, C, D. Here A, B, C, D, A, B, C, D. So it will keep on repeating as the branches continues. So for numerous branches, you can see that the same state will repeat. This is the significance of the code tree. Here actually we have only 2 flip-flops in this encoder. So after the third branch, irrespective of this input, the state would get repeated. And since this diagram looks complex, let us just simplify this diagram by folding this tree with the same states together. That means wherever I have this A, let me just fold it in order to get into another simple diagram called as trellis diagram. Here in the code tree, the numerous branches are there. Instead, in the trellis diagram, we are going to fold these branches of the tree to form a simplified diagram where we'll have only 4 rows, each representing the states of the tree. That is A, B, C, D. Only 4 rows will be there. And now here the depth of this trellis diagram, that is the levels, we call this as level. It can go to any extent. Once you construct this trellis diagram, it is just mere concatenation of the trellis diagram when the number of branches, when the number of bits is extended. Now, how to construct this trellis diagram? Once again, we follow the same state diagram. So let us have this state diagram on the side of it. Now, we are starting with the state A. Always the initial state will be all zero state. So the state is A, and now when the input is 0, it remains in the same state, producing an output of 0, 0. So the next state would be, here also we follow the same convention. Solid line indicates an input of 0 and dashed line indicates an input of 1. So when an input of 0 is encountered, the next state also is A. So we are in the same row, producing an output of 0, 0. Producing an output of 0, 0. And now from state A, if the input is 1, then we follow this dashed line. It goes to state B, producing an output of 1, 1. So the next state is state B. This is the second state. This is the first state. This is the second state. It goes like this. So the next state is state B. This is when an input of 1 is encountered. The next state is B, producing an output of 1, 1. producing an output of 1, 1. Right. And now we are in state B. We are in state B. When an input of 0 is encountered, you come to state C, producing an output of 1, 0. Producing an output of 1, 0. So here, solid line, you are coming to state C. You are in state B. Now, the next state happens to be state C. Solid line, that is input of 0, producing an output of 1, 0 here. This 1, 0 here. And from the same state B, if the input is 1, you go to state D. If the input is 1, you go to state D, producing an output of 0, 1. So from B, the next state would be D. This is a second state. Now this is a third state we are talking about. So from state B, you are coming to state D, producing an output of 1. Since it is a message bit is 1, the dash line is used here to construct the trellis diagram. So from B, input of 0, go to state C with an output 1, 0. From B, the next state is D, producing an output of 0, 1 when an input is 1. Right. And then now coming to state C. Here you are in state C. When an input of 0 is encountered, it comes to state A, producing an output of 1, 1. From here, C, when an input of 0 is encountered, it goes to state A with an output of 1, 1. And then from C, if an input of 1 is encountered, go to state B, producing an output of 0, 0. From state C, with an input of 1, you go to state B, producing an output of 0, 0. Now coming to state D, here, state D, when the input is 0, come to state C, producing an output of 0, 1. From state D, come to state C here, come to state C for an input of 0, that is solid line, producing an output of 0, 1. So, take a solid line, go to state C with an output of 0, 1. From state D, if the input is 1, go to state D itself, producing an output of 1, 0. So, from state D, dash line, that is input of 1, go to state D itself, producing an output of 1, 0. So the same thing needs to be repeated from all points. So from A, it goes to state A, it goes to state A like this, producing an output of 0, 0. From state A, if you encounter 1, it goes to state B. The next state would be state B, producing an output of 1, 1. Then from B, if you get an input of 0, it comes to state C. So it comes to state C from all the state B, producing an output of 1, 0. And from state B, if the input is 1, come to state D, producing an output of 0, 1. Similarly, from state C, if the input is 0, go to state A always, producing an output of 1, 1. From state C, if the input is 1, go to state B, producing an output of 0, 0 always. From state D, if the input is 0, go to state C always, producing an output of 0, 1. And from state D, if the input is 1, go to state D itself, producing an output of 1, 0. So this trellis diagram can now be constructed using this state diagram, and we can see that all the state A's are present here. Compare it with the code tree, all the state A's are here, B's are here, C's are here, and D's are here. Having constructed the trellis diagram, how to encode the given message sequence. Let us take the same message sequence 10011. So from the all zero state you start. Given the first bit is 1, so follow the dash line. Now here you are in state B with producing an output of 1 1. And now the next message bit is 0. From here follow the solid path. Here you are in state C with an output of 1 0. And then from here the next bit is 0. So follow the solid path. Here you are with an output of 1 1. And from here the next message bit is 1. So follow the dash line. Here you are with an output of 1 1. And from here you are taking a message bit of 1. So follow the dash line. You are coming to state D with an output of 0 1. So it goes like this. So simply you can traverse through this trellis diagram in order to find the encoded output. This is about your convolutional codes. So here we have 4 ways of finding out the convolutional code. One is the polynomial method, then the code tree method, state diagram method, and the trellis diagram. First you have to draw the state diagram by assigning the initial states. Draw the state diagram where you will be getting the next state outputs and the corresponding outputs. From the state diagram you can draw the code tree as well as the trellis diagram.